a spacecraft has already flown through the ocean of Enceladus, not metaphorically but literally, through water vapor erupting from beneath its ice, and found hydrogen organic molecules and the chemical signature of hydrothermal vents on the seafloor. Subscribe, there's a new one every few days. Welcome to white space. No rush, just the cosmos. There is a moon orbiting Saturn that may be the most consequential object in the entire solar system. Not because of its size, it is modest, barely 500 kilometers across, but because of what lies beneath its surface. Enceladus is covered in a shell of bright white ice, and for years scientists assumed it was little more than a frozen inert fragment of the outer solar system. Its surface reflects nearly all sunlight that strikes it, giving it an albedo of approximately 1.4, a figure that seems impossible until you understand it results from freshly deposited ice continuously replenishing the surface. Nothing about its appearance from a distance suggested anything unusual. Then, in 2005, the Cassini spacecraft flew over its southern pole and everything changed. The discovery did not begin with the cameras. It began with the magnetometer. During Cassini's third flyby of Enceladus in July 2005, the instrument detected a distortion in Saturn's magnetic field, a deflection consistent with ionized gas being injected into the local environment from a source near the South Pole. The plasma science instruments confirmed the presence of water ions. Only when the images caught up did the full picture emerge. Enormous plumes of water vapor and ice particles erupting from a series of long parallel fractures in the southern polar terrain. These features, now called the Tiger Stripes, run roughly 130 kilometers in length, separated by about 35 kilometers, and are warmer than the surrounding terrain by approximately 90 degrees Celsius as measured by the composite infrared spectrometer. They radiate heat at a rate of approximately 15 gigawatts. For a moon less than 500 kilometers across, that is a staggering thermal output. The water is not ancient. It is being generated now, driven upward from a liquid saltwater ocean concealed beneath an ice shell that varies from roughly 2 kilometers thick directly over the Tiger Stripes to 25 or 30 kilometers thick elsewhere. The first hints that the ocean existed came from measurements of Enceladus's libration, a subtle wobble in its rotation, which was too large to be consistent with a solid body. A global subsurface ocean, partially decoupled from the ice shell above it, would produce exactly the libration amplitude Cassini measured. Gravity measurements during close flybys refined the picture. The ocean is concentrated toward the South Pole and may reach a depth of roughly 10 kilometers, sitting atop a rocky seafloor. Cassini flew directly through the plume 17 times across the duration of its mission, collecting samples that grew richer in detail with each pass. The mass spectrometer found water, carbon dioxide, methane, molecular nitrogen, hydrogen, cyanide, and ammonia. In 2008, the instruments detected silica nanoparticles, grains of silicon dioxide between 2 and 8 nanometers in size, forming only when liquid water at temperatures above 90 degrees Celsius dissolves silica from rock and then reprecipitates it as the fluid cools and rises. This was the first direct evidence for active hydrothermal chemistry. In 2017, a paper in the journal Science announced the detection of molecular hydrogen in the plumes at concentrations implying continuous production, the unmistakable signature of ongoing serpentinization, the reaction of hot water with iron and magnesium-bearing rock that produces hydrogen as a byproduct. And in 2018, a paper in Nature reported the identification of complex organic molecules in the plumes with masses exceeding 200 atomic mass units, including compounds with nitrogen and oxygen-bearing functional groups, the same structural categories as amino acids and other molecules central to terrestrial biochemistry. The implications are difficult to overstate on Earth. The combination of liquid water, a chemical energy source, and organic compounds is the minimum set of conditions associated with life. All three are present in the ocean of Enceladus. The hydrothermal vents at the seafloor produce hydrogen that serves as an energy source for chemosynthetic microorganisms. Those organisms on Earth form the base of entire ecosystems independent of sunlight, at depths and pressures and temperatures where nothing was expected to live before their discovery in 1977. The hydrothermal vent fields at mid-ocean ridges have now been found to host biomass densities comparable to soil. If the same principle applies at Enceladus, the ocean beneath the ice could be biologically active. There are important unknowns. The ocean is believed to be relatively young, perhaps only a few 100 million years old, sustained by tidal heating that may be episodic rather than constant. Whether that timescale is sufficient for life to originate independently rather than simply persist if seeded from elsewhere is an open question. The salinity of the ocean, estimated from the ion composition of the plumes, is roughly similar to that of Earth's oceans, a somewhat reassuring parallel, since extreme salinity can be biochemically hostile, and the pH appears to be mildly alkaline between 8.5 and 10.5, consistent with the serpentinization environment and within the range tolerated by many terrestrial microorganisms. What makes Enceladus particularly accessible is that the plumes provide a natural sampling mechanism. A spacecraft does not need to land, drill through ice, or carry a submarine. It only needs to fly through the plumes and collect material. The Cassini mission demonstrated this was technically feasible. A proposed successor, the Enceladus Orbolander concept studied at Johns Hopkins Applied Physics Laboratory, would enter orbit around Enceladus and conduct extended plume sampling before descending to the surface for a landed science phase. The mission was ranked as a high-priority medium-class mission in the 2022 Decadal Survey. Whether it will fly and when depends on budget cycles and the competing priorities of a decade full of other compelling destinations, but the scientific case is perhaps the strongest in the solar system for any mission aimed at the question of extraterrestrial life. The answer may be only a flyby away. The innermost planet of our solar system presents a very different kind of challenge. Mercury sits just 58 million kilometers from the Sun at its closest approach, and that proximity creates a blinding observational problem from Earth. The planet never strays more than 28 degrees from the Sun in the sky. It is never visible in a dark sky. From ground level, it is always seen against the twilight glow of dawn or dusk, low on the horizon, filtered through a thick column of atmosphere that smears and dims its light, even from space. The Hubble Space Telescope has never been used to observe Mercury. Doing so would require pointing it so close to the Sun that concentrated sunlight could destroy its optical systems in seconds. The telescope's scheduling software includes a hard prohibition against Mercury observations. The first detailed knowledge of Mercury's surface came from radar, not optics. Beginning in the 1960s, astronomers at Goldstone in California and at Arecibo in Puerto Rico bounced radio pulses off the planet and measured the returning echoes. The Doppler shift of the reflected signal revealed the rotation rate, and the answer was surprising. Mercury does not keep one face permanently turned toward the Sun, as tidal locking would suggest for a body so close to such a massive star. Instead, it completes exactly 3 rotations for every 2 orbits. A 3-2 spin orbit resonance, the first such resonance discovered anywhere in the solar system and the result of a complex interplay between Mercury's slightly elliptical orbit and its internal mass distribution. This was established definitively in 1965, overturning a consensus that had prevailed for decades based on flawed optical observations. Radar also established the temperature of the surface, more than 400 degrees Celsius on the sun-facing side, and later identified anomalously reflective regions near the poles consistent with ice. The first spacecraft to visit Mercury was Mariner 10, launched in November 1973. It became the first probe to use a gravitational assist maneuver, swinging around Venus in February 1974 to redirect toward Mercury. It made 3 separate flybys in 1974 and 1975, covering about 45% of the planet's surface in photographic detail. Mariner 10 discovered that Mercury possesses a global intrinsic magnetic field, an entirely unexpected finding for such a small, slowly rotating body, since the dynamo theory of planetary magnetic fields at the time predicted that only rapidly rotating planets with conducting fluid interiors could generate sustained magnetic fields. Mercury rotates once every 58.6 Earth days. By any standard model, it should not have a field, yet it does approximately 1% as strong as Earth's, but clearly dipolar and global, deflecting the solar wind sufficiently to create a small but genuine magnetosphere. Mariner 10 was placed in a heliocentric orbit after its fuel ran out and is believed to still be in that orbit today. For nearly 30 years, no spacecraft returned to Mercury. The difficulty of reaching it, requiring so much fuel to slow down against the Sun's gravity that conventional mission architectures are barely feasible, kept it off the priority list despite the mysteries Mariner 10 had left unanswered. When Messenger was finally approved and launched in August 2004, the trajectory engineers designed a route that reduced fuel requirements by using 6 gravity assists over 6.5 years, 1 past Earth, 2 past Venus, and 3 past Mercury itself. Each Mercury flyby was used as an opportunity to observe previously unmapped terrain, and each one returned significant new findings before the spacecraft even achieved orbit. Messenger entered orbit around Mercury on March 18, 2011, and immediately began transforming the planet from a half-understood mystery into a documented world. One of its first major discoveries was a class of surface features called hollows, shallow, irregular depressions with bright interiors and halos, typically tens to hundreds of meters deep and ranging from a few meters to several kilometers across. They occur on crater floors, on central peaks, and on ejecta blankets across Mercury's surface. And they are actively forming. The leading hypothesis is that they form through sublimation, the direct conversion of volatile material from solid to vapor when exposed to sunlight and the intense particle radiation near the sun. What volatile material remains in Mercury's crust at these low latitudes and under these extreme conditions is itself puzzling. The conventional picture of Mercury as a thermally processed, volatile, depleted body is inconsistent with the ongoing loss processes implied by the hollows. The magnetic field turned out to be even stranger on close inspection than Mariner 10 had suggested. Messenger's high-resolution magnetometer measurements established that Mercury's magnetic dipole is offset northward from the planet's geometric center by about 0.2 planetary radii, an asymmetry that causes the field to be significantly stronger at the North Pole than at the South. This offset has no analog in any other planetary magnetic field in the solar system. It may reflect unusual fluid dynamics in Mercury's liquid outer core, or it may indicate that Mercury's dynamo is operating in a regime fundamentally unlike anything we model from Earth's interior. The magnetic field also interacts with the solar wind in a way unique to Mercury. Because the planet's magnetosphere is so small, energetic solar wind particles regularly reach the surface, sputtering atoms from the rock and feeding Mercury's tenuous exosphere with sodium, calcium, magnesium, potassium, and other species. This process gives Mercury a faint comet-like sodium tail that extends downwind for millions of kilometers, observable from Earth-based spectrographs as a faint emission line in the planet's wake. The volatile inventory of Mercury's surface represents one of the central unresolved puzzles in planetary science. Standard thermal models of the inner solar system predict that a planet formed so close to the Sun should have been too hot to retain significant quantities of sulfur, potassium, sodium, or chlorine, elements that condense and remain solid only at relatively low temperatures. Yet Messenger's X-ray spectrometer found these elements at the surface in concentrations comparable to far cooler planetary bodies. Either Mercury formed in a different part of the solar system and migrated inward, or the giant impact hypothesis for Mercury's core formation. The idea that the massive collision stripped away most of the mantle, leaving a disproportionately large iron core, is incomplete or incorrect. The core accounts for roughly 83% of Mercury's total mass, an extraordinary fraction by any comparison. Earth's core represents only about 32% of its mass. The origin of this difference is one of the key questions the Bepi-Colombo mission is designed to address. Messenger mapped the full surface and produced the first complete global geological map of Mercury, identifying volcanic plains that cover perhaps 27% of the surface, enormous lobate scarps, thrust faults up to 3 kilometers high and hundreds of kilometers long, that formed as the planet cooled and contracted by as much as 7 kilometers in radius over its history, and impact structures ranging from tiny fresh craters to the multi-ring Caloris Basin, 1,550 kilometers across, whose formation energy was sufficient to fracture the crust completely and raise terrain on the antipodal point on the opposite side of the planet. The antipodal region, called the chaotic terrain, is a jumbled landscape of hills and valleys created by seismic waves converging at the point directly opposite the impact. In its final months, as fuel ran low, Messenger's orbit decayed progressively lower. Engineers used the helium gas remaining in the propulsion system as improvised thruster propellant, a maneuver without precedent in deep space operations, buying months of additional science at orbital altitudes, sometimes less than 25 kilometers above the surface, close enough to resolve features smaller than a swimming pool. On April 30, 2015, the improvisation ran out. Messenger struck the surface at 14,000 kilometers per hour, leaving a fresh crater approximately 16 kilometers in diameter. The third Mercury mission, Bepi-Colombo, a joint project of ESA and the Japan Aerospace Exploration Agency, launched in October 2018 and is currently completing its approach sequence. It carries 2 orbiters that will separate and enter different orbits upon arrival in 2025, the Mercury Planetary Orbiter, focused on surface geology, geochemistry, and interior structure, and the Mercury Magnetospheric Orbiter, focused on the magnetic field and space environment. Their combined instrument suite represents a generational leap beyond Messenger. The questions Messenger raised about the origin of hollows, the nature of the asymmetric magnetic field, the mystery of Mercury's volatile inventory are questions Bepi-Colombo was designed to answer. Further out in the solar system, a spacecraft has spent years trying to understand why one of the most Earth-like planets in some respects became so hostile. Mars today is cold, dry, and blanketed in an atmosphere so thin. About 1% of Earth's surface pressure, that liquid water cannot persist on its surface. It would evaporate almost instantaneously. But the geology tells another story, written across billions of years in ancient riverbeds, delta deposits, shoreline terraces, and mineral assemblages that form only in the presence of standing water. Phyllosilicates, clay minerals that require prolonged contact with liquid water to form, have been identified from orbit across widespread regions of the ancient Martian highlands, concentrated in rock formations that predate approximately 3.5 billion years ago. Sulfates, which form in evaporating water bodies, are found extensively in younger formations. The chemical record of Mars is a record of progressive drying, played out over 1 billion years of planetary history. The MAVEN spacecraft, Mars Atmosphere and Volatile Evolution, arrived in September 2014 with a specific mandate: determine where the atmosphere went and how quickly. What it found was a continuous, ongoing process driven primarily by the solar wind. Without a strong global magnetic field to deflect the stream of charged particles flowing outward from the Sun, Mars is directly exposed to this bombardment. MAVEN measured atmospheric escape rates directly by flying through the upper atmosphere during its highly elliptical orbit, directly sampling the ion populations and measuring their velocities. Under quiet solar conditions, Mars loses roughly 100 grams of atmosphere per second. During major solar storms, periods when the Sun ejects billions of tons of magnetized plasma in what are called coronal mass ejections, this rate increases by a factor of 10 to 20 or more. MAVEN also provided the most detailed measurements ever made of the isotopic composition of the Martian atmosphere. Isotopes of the same element behave identically in chemistry, but differ slightly in mass. And this mass difference means that lighter isotopes escape the atmosphere slightly faster than heavier ones. By measuring the current enrichment of heavy isotopes deuterium relative to ordinary hydrogen carbon-13, relative to carbon-12, argon-38 relative to argon-36, MAVEN's instruments allowed reconstruction of how much atmosphere Mars has lost over its history. The deuterium to hydrogen ratio in the Martian atmosphere is approximately 5 times higher than in Earth's oceans, implying that Mars has lost approximately 87% of its original water inventory to space. Combined with the geological evidence for ancient rivers and lakes, this suggests that early Mars may have had enough water to cover its entire surface to a depth of 20 to 100 meters, a shallow but globally significant ocean that evaporated and was stripped away over billions of years. One finding from MAVEN that received less public attention but carries significant implications for planetary habitability was the discovery that Mars once had a global magnetic field. The evidence comes not from the atmosphere, but from the rocks. Patches of strongly magnetized ancient crust are detectable from orbit. Remnant fields frozen into rock as it cooled in the presence of a magnetic dynamo that ceased operation roughly 4 billion years ago. When that dynamo failed, possibly because the planet's small iron core solidified and could no longer sustain convective fluid motion, the magnetic shield disappeared, leaving the atmosphere directly exposed to the solar wind. MAVEN's measurements allow the rate of atmospheric loss under a shielded versus an unshielded Mars to be compared. The conclusion is that the magnetic field's disappearance was not merely correlated with Mars's atmospheric loss, it was causal. Mars may have been habitable while its dynamo operated. Its habitability ended when the core solidified. Alongside MAVEN's atmospheric work, a separate mission was probing Mars from the surface in a completely different way. The InSight lander, which touched down in November 2018 on the broad volcanic plain called Elysium Planitia, carried a seismometer of extraordinary sensitivity, capable of detecting ground motions smaller than the diameter of an atom. Over 4 years of operations before dust accumulation finally depleted its solar panels in December 2022, InSight detected more than 1,300 seismic events or Marsquakes. The seismometer data allow the first direct measurements of Mars's internal structure. A crust between 24 and 72 kilometers thick, with significant regional variation, a mantle extending to about 1,500 kilometers depth, and a liquid iron core approximately 1,830 kilometers in radius. The core's radius was larger than pre-mission predictions had suggested, implying that the iron is alloyed with lighter elements oxygen, sulfur, hydrogen, or carbon. That reduces its average density. This matters for understanding why Mars's core solidified and its magnetic field failed. The composition and cooling rate of the core determine how long it remains liquid and convective. The surface of Mars is currently hosting the most capable robotic explorer ever built. Perseverance landed in Jezero crater in February 2021, targeting a site chosen specifically for its record of ancient water activity. Jezero is the remnant of an ancient lake basin that was fed by a river flowing from the west, depositing a fan-shaped delta of sediment at the lake's edge. Over roughly 3.5 billion years, the lake dried, the sediment lithified, and erosion gradually exposed the layered rock of the delta front, precisely the rock that is most likely to have concentrated and preserved any biosignatures that existed in the ancient Martian environment. Perseverance has drilled into this material and found organic molecules, including aromatic compounds and aliphatic chains, the building blocks of carbon chemistry in multiple targets. The presence of organics on Mars is not itself evidence of life. Organics are delivered to planetary surfaces continuously by meteorites and form abiotically through known geochemical processes. But their concentration in lacustrine sediments alongside minerals like carbonates and sulfates that indicate a chemically active aqueous environment means these rocks are exactly the sample targets scientists had hoped for. The MOXIE instrument aboard Perseverance, the Mars Oxygen In Situ Resource Utilization Experiment, demonstrated the production of oxygen from the Martian atmosphere by solid oxide electrolysis of carbon dioxide. During its operational campaign between 2021 and 2023, MOXIE produced a total of approximately 122 grams of oxygen across 16 operational runs at purity levels exceeding 98%. At full scale, a system based on MOXIE's design could produce the metric tons of oxygen required for a human mission's rocket propellant and life support. The demonstration established that in situ resource utilization at Mars is not merely theoretically possible, but technically mature enough to plan around. Alongside Perseverance came Ingenuity, a solar-powered rotorcraft helicopter weighing 1.8 kilograms, designed to demonstrate powered flight in the thin Martian atmosphere. Its carbon fiber blades spin at 2,400 rotations per minute, roughly 5 times faster than a helicopter blade on Earth, to generate sufficient lift in air 1% as dense as Earth at sea level. The first flight, on April 19, 2021, lasted 39 seconds and reached an altitude of 3 meters. What was planned as a 5-flight technology demonstration extended to more than 70 flights and nearly 3 years of operations, during which Ingenuity covered more than 17 kilometers of total distance, reached altitudes of up to 24 meters, and achieved airspeeds of up to 8 meters per second. It served as an aerial scout for Perseverance, surveying terrain, identifying candidate sample targets, and demonstrating that the marginal atmospheric conditions sufficient for a 1.8 kilogram drone are also sufficient for much larger aircraft. The successor architecture, a helicopter roughly the size of a sports utility vehicle, proposed under the name Mars Science Helicopter, would be capable of carrying scientific payloads comparable to a small rover, accessing terrain entirely unreachable by wheeled vehicles. Some of the most surprising discoveries in recent solar system exploration have come not from planets or moons, but from small bodies we once regarded as largely uniform and geologically dead. The near-Earth asteroid Ryugu is a rubble pile, a loose aggregation of material held together primarily by gravity rather than structural strength, roughly 900 meters in diameter, shaped like a spinning top with a prominent equatorial ridge. Its surface is almost uniformly dark, reflecting only about 2 to 3% of incoming sunlight, making it one of the darkest objects in the solar system. When the Japanese spacecraft Hayabusa 2 arrived in June 2018, after a 3.5-year journey, the science team's first challenge was finding a landing site that was flat and clear enough for a safe touchdown. Ryugu's surface was covered in boulders, many of them larger than the spacecraft itself. The mission planners had expected a smooth, sandy regolith. Instead, they found a landscape of closely packed rubble that forced a complete re-evaluation of the landing plan. The mission deployed multiple surface packages. Mascot, the Mobile Asteroid Surface Scout, a lander built by the German Aerospace Center in collaboration with the French space agency CNES, was released in October 2018 and bounced across the surface for 17 hours on battery power before going silent. During that time, it measured the thermal properties of the surface, finding that heat propagated downward far more slowly than expected, suggesting a surface layer of extremely porous, fragile material with an insulating structure similar to aerogel. Its spectrometer found a surface mineralogy dominated by hydrated silicates and darker organic compounds, with no evidence of the fine dust predicted to accumulate on asteroid surfaces from meteorite gardening. Two small Japanese rovers, Minerva 21A and Minerva 21B, hopped across the surface using internal spinning masses, taking hundreds of photographs and temperature readings from the surface itself. The first mobile surface explorers ever to operate on an asteroid. The most dramatic event of the mission was the small carry-on impactor, deployed in April 2019. A shaped copper charge detonated to fire a 2.5 kilogram copper projectile into the surface at 2 kilometers per second. The impact excavated a crater approximately 10 meters wide, exposing subsurface material that had never been in contact with the space environment. Before the ejector settled, Hayabusa 2 photographed the crater from a safe vantage point and then descended into it twice at different times to collect material from the undisturbed substrate. The spacecraft made 2 separate surface touchdowns, in all each contact lasting mere seconds, using a horn-shaped collection mechanism that fired a tantalum pellet into the surface to spray material upward into the sample container. The total sample mass returned to Earth was 5.4 grams, less than a teaspoon, but it was the most carefully provenance-tracked extraterrestrial material ever collected. The sample capsule landed in the Australian outback in December 2020. Initial analyses published in 2021 and 2022 across multiple journals revealed a chemistry of extraordinary complexity and antiquity. The Ryugu material contains hydrated minerals, phyllosilicates, indicating that liquid water was present within the asteroid at some point in its early history, probably within the first 10 million years of solar system formation, when radiogenic heating from short-lived isotopes like aluminum-26 could melt ice within the body. The samples contain amino acids including glycine, alanine, valine, and isoleucine, all found in terrestrial proteins, as well as dozens of other amino acid species not used by terrestrial biology. The isotopic signatures of the amino acids indicate an extraterrestrial origin, ruling out terrestrial contamination. Polycyclic aromatic hydrocarbons, aliphatic hydrocarbons, and soluble organic compounds of remarkable variety are present throughout the sample. And the deuterium to hydrogen ratio of the water locked in the hydrated minerals closely matches the isotopic signature of Earth's oceans, consistent with the hypothesis that water-rich carbonaceous asteroids like Ryugu's parent body delivered a significant fraction of Earth's water inventory during the early bombardment period. Perhaps most striking is the evidence that much of Ryugu's organic chemistry predates the solar system itself. Isotopic anomalies in certain compounds, ratios of carbon, nitrogen, and sulfur isotopes that differ from the values set by nucleosynthesis in the sun's parent molecular cloud, indicate that these molecules were inherited from presolar grains that survived the formation of the solar system intact. They were present in the interstellar medium before the Sun existed, incorporated into the planetesimals that built the asteroid belt, and are now 4.6 billion years later, sitting in laboratory dishes in Japan and being analyzed by mass spectrometers. The continuity between interstellar chemistry and the chemistry of life's building blocks, suggested for decades and confirmed by the Ryugu samples, implies that the organic inventory necessary for life's origin is not something that had to be synthesized on Earth, but was delivered as a cosmic inheritance. Hayabusa 2 did not end its mission with the sample return. Using fuel reserves accumulated through careful planning, the spacecraft redirected toward a second target, the tiny asteroid 1998 KY26, a near-Earth object approximately 30 meters in diameter with an unusually rapid rotation rate of about 10 minutes, fast enough that loose surface material would be flung off by centrifugal force. The spacecraft is expected to arrive in 2031. In parallel, NASA's OSIRIS-REx mission, which sampled the asteroid Bennu in 2020 and returned its capsule to Earth in September 2023, has been renamed OSIRIS-APEX and redirected toward the asteroid Apophis, the near-Earth asteroid that will pass within 32,000 kilometers of Earth's surface in April 2029. Close enough to be visible to the naked eye, Apophis will be the most closely studied small body in solar system history during those weeks of approach. In the asteroid belt between Mars and Jupiter, a spacecraft arrived at destinations most planetary scientists had assumed would prove relatively uninteresting, and proceeded to overturn that assumption at nearly every location it visited. The Dawn spacecraft was the first mission ever to orbit two extraterrestrial bodies in sequence, a feat made possible by its ion propulsion system. 3 xenon ion engines that accelerated ions to 30 kilometers per second, producing a thrust of about 90 millinewtons continuously, far less than the weight of a sheet of paper, but sustained over months and years to accumulate the velocity changes that chemical rockets accomplish in minutes. The efficiency of ion propulsion, measured in specific impulse, the amount of thrust produced per unit of propellant is roughly 10 times greater than chemical rockets, allowing Dawn to perform orbital insertions and departures that would be physically impossible with conventional technology. Dawn launched in September 2007 and arrived at the large asteroid Vesta in July 2011, becoming the first spacecraft to orbit a main belt asteroid. Vesta is differentiated. It melted and separated into a metallic core, silicate mantle, and basaltic crust within the first few million years of solar system history, while short-lived radioactive isotopes were still producing heat. This makes Vesta geologically more similar to a small terrestrial planet than to a typical primitive asteroid. Its south pole is dominated by 2 overlapping giant impact basins. The older Venenia Basin, roughly 400 kilometers across, overlaid by the younger Reisilvia Basin, 500 kilometers in diameter, and nearly 20 kilometers deep. The central peak of Reisilvia rises 22 kilometers from the basin floor, making it one of the tallest mountains in the solar system. The impacts that formed these basins excavated material from Vesta's interior and launched enormous quantities of ejecta into interplanetary space. Over billions of years, that material has been delivered to Earth as meteorites. The hedged meteorites, Howardites, Eucrits, and Diogenites are identified by their distinctive oxygen isotope ratios and mineral compositions as material from Vesta, and they constitute roughly 5% of all meteorite falls in terrestrial collections. Dawn confirmed this connection directly by finding matching spectral signatures at the surface. Dawn departed Vesta in September 2012 and entered orbit around Ceres in March 2015. Becoming the first spacecraft to orbit a dwarf planet, arriving several months before New Horizons reached Pluto. Ceres is the largest object in the asteroid belt, approximately 940 kilometers in diameter, with a bulk density suggesting a substantial water-ice component, perhaps 25% by mass. Its surface is almost uniformly dark, coated with a mixture of hydrated silicates, carbonates, and organic material that absorbs most incoming sunlight. But concentrated in Okator crater, a 90-kilometer impact structure about 4 kilometers deep, formed roughly 22 million years ago, are a series of bright deposits whose reflectivity stands in stark contrast to the surrounding terrain. The brightest feature in Okator, and in the entire solar system relative to its immediate surroundings, is Sterealia facula, a central mound of bright material approximately 9 kilometers wide and 400 meters high. Dawn's spectrometers identified the composition as sodium carbonate mixed with ammonium chloride and hydrohalite, or sodium chloride dehydrate, minerals that precipitate when a brine evaporates in near vacuum conditions. The brine appears to have come from a subsurface reservoir. Gravity measurements during Dawn's low-altitude mapping phase indicated that Okator sits above a region of anomalously low density, consistent with a partially liquid brine pocket, and thermal modeling of the impact suggests that the energy deposited by the crater-forming event would have created a liquid water reservoir that has been slowly draining to the surface ever since, leaving evaporite deposits as the brine vaporizes and refreezes. The most recent activity in Okator may be only a few hundred years old. Dawn's observations showed that the bright materials in the crater appear younger in ultraviolet imaging than the surrounding terrain, suggesting ongoing deposition. Ceres also bears a structure called Ahuna Mons, a steep-sided dome approximately 4 kilometers tall and 17 kilometers wide, sitting in isolation on a broad plain with no obvious structural relationship to surrounding terrain. There are no impact craters on its surface, confirming that it formed recently in geological terms. Ahuna Mons is almost certainly cryovolcanic, a dome formed when a viscous mixture of brine, salts, and ice was forced upward through the crust and pulled at the surface, unable to flow far before solidifying. The rate at which such a dome should relax and flatten under its own weight, a process called viscous relaxation, allows an age estimate. Ahuna Mons is believed to have formed within the last 200 million years. Planetary scientists suspect there are older, flattened domes elsewhere on Ceres that have relaxed beyond recognition. Ahuna Mons simply happens to be young enough to still be recognizable. Dawn's discovery of organic compounds in Ernutet crater, reported in 2017, added another layer of complexity. The organics, identified by their spectral absorption features at infrared wavelengths consistent with aliphatic and aromatic carbon compounds, are concentrated in patches on the crater floor and walls, not uniformly distributed, suggesting an endogenous source, rather than delivery by an impacting carbon-rich asteroid. If the organics formed within Ceres itself, it implies that the dwarf planet hosts an active organic chemistry driven by its internal water, heat, and carbon inventory, a miniature version of the same processes thought to operate in bodies like Enceladus and Europa. Ceres, in this reading, is not a dead asteroid belt remnant, but a surviving ocean world, geologically quieter than its more dramatic counterparts, but chemically active, preserving in its briny subsurface a record of early solar system water chemistry. Dawn ran out of hydrazine attitude control fuel in October 2018, ending its ability to point its antenna toward Earth. It entered a stable final orbit around Ceres with a lifetime of at least 20 years before orbital decay might cause a surface impact. It is now a permanent artificial satellite of the first dwarf planet ever explored, orbiting silently above the bright spots of Okator crater. Beyond Jupiter lies a system so vast and so complex that a single spacecraft spent 13 years exploring it and still returned scientific surprises in its final weeks. Cassini entered Saturn orbit in July 2004, becoming only the second spacecraft to achieve orbit at an outer planet after Galileo at Jupiter. It carried the Huygens probe built by the European Space Agency, which separated from the main spacecraft on Christmas Day 2004 and spent 3 weeks coasting to Titan before entering its atmosphere on January 14, 2005. The Huygens descent lasted about 2 hours and 20 minutes. The probe fell through a thick orange haze of nitrogen and complex organic molecules called tholins, polymeric compounds built from nitrogen and methane through ultraviolet photochemistry in the upper atmosphere, before descending into clearer air below 50 kilometers altitude. At an altitude of roughly 25 kilometers, the probe's cameras began resolving features on the surface, branching dark channels that looked unmistakably like drainage systems, flowing toward lighter lowland regions. The probe landed on a surface of rounded pebbles, each a few centimeters across and dark worn smooth by flowing liquid. Not water, but liquid methane. The landing site, later identified as a dry riverbed in a region named the Adiri region, recorded a temperature of minus 179 degrees Celsius and an atmospheric pressure of 1.47 times Earth's at sea level. The probe detected a brief whiff of methane from the warm footpad vaporizing the surface material on contact. The microphone aboard Huygens recorded wind sounds during the descent. Processed into audio and released to the public in 2005, the first sound ever captured in the atmosphere of another world. It was a faint, steady hiss against the background of quiet alien air. Over the following 8 years of Cassini's primary and extended missions, the spacecraft completed 127 Titan flybys, each revealing new aspects of the Moon's extraordinary complexity. Titan's methane cycle, the atmospheric equivalent of Earth's water cycle, operates through evaporation, cloud formation, precipitation, surface flow and collection in lakes and seas. The largest hydrocarbon sea, Kraken Mare, covers an area of approximately 400,000 square kilometers, larger than the Caspian Sea, concentrated near the North Pole. Ligeia Mare, the second largest, has been measured by radar altimetry to be at least 8 meters deep at its center, with measurements suggesting a composition of roughly 71% ethane, 12% propylene, and 17% nitrogen dissolved in methane and other compounds. The radar return from the sea surface is mirror smooth, indicating an absence of wind-driven waves, consistent with wind speeds at the surface measured by Huygens at less than 1 meter per second. Titan's seasons last approximately 7 years, 1/4 of its 29.5-year orbital period around the Sun, and Cassini was present long enough to observe the transition from southern summer to northern summer, watching methane clouds migrate from one hemisphere to the other and the northern polar lakes expand as spring brought evaporation from the southern lakes. This seasonal exchange of methane between hemispheres is believed to drive a slow global circulation, and the long-term methane balance of Titan poses a fundamental question. Methane in the atmosphere is destroyed by ultraviolet photolysis on a timescale of roughly 30 million years, producing tholins and other stable compounds that accumulate as sediment. For methane to still be present in Titan's atmosphere after 4.6 billion years, it must be continuously replenished. The likely source is cryovolcanism, eruptions of methane-rich material from the interior, but direct evidence for active cryovolcanic eruptions on Titan has proved elusive, and the question of Titan's methane budget remains one of the most significant open problems in outer solar system science. Titan also has a subsurface liquid ocean, not of methane but of water. The evidence comes from measurements of Titan's tidal deformation. As Titan orbits Saturn, the planet's gravity raises a tidal bulge in the Moon's surface that travels with it through its orbit. The amplitude of this deformation, measured by tracking changes in Cassini's orbital path during repeated Titan flybys, is 10 times larger than expected for a purely solid body. A layer of liquid water between the ice shell and the rocky interior, would explain the deformation by allowing the shell to flex more freely. The ocean is likely ammonia-rich. Ammonia acts as an antifreeze, lowering the melting point of water sufficiently to maintain liquid conditions at Titan's deep interior temperatures. Unlike Enceladus, this ocean appears to have no contact with the rocky seafloor, insulated above by a thick ice shell and possibly below by a layer of high-pressure ice, which would limit the hydrothermal chemistry that makes Enceladus so astrobiologically compelling. But it adds Titan to the growing list of outer solar system bodies with subsurface liquid water. The mission now building on Cassini's Titan discoveries is Dragonfly, a rotorcraft lander designed and built at Johns Hopkins Applied Physics Laboratory, selected by NASA in 2019 and currently scheduled for launch in 2028. Dragonfly is a dual quadrotor, roughly the size of a small car, capable of flying up to 8 kilometers in a single flight, using the abundant atmospheric density that makes rotorcraft viable on Titan despite its lower gravity. It will land in Titan's Shangri-La dune fields, a region of large linear dunes composed of organic sediment, and conduct detailed chemical analysis of the surface before flying progressively toward its primary science target, Selk Impact Crater. Selk is approximately 90 kilometers in diameter, and impact events of that scale would have melted the surface ice, producing a transient liquid water environment, lasting perhaps hundreds to thousands of years, long enough. Some researchers argue for prebiotic chemistry to proceed. The crater floor and walls contain frozen deposits of the organic water mixture that existed during the impact melt phase. Dragonfly will sample this material and attempt to determine how far the chemistry has progressed toward biological complexity. The mission represents a fundamental shift in the philosophy of outer solar system exploration. Rather than a single fixed lander, Dragonfly is a mobile platform that can visit multiple scientifically distinct sites across original traverse. Saturn's moon system is not only Titan and Enceladus. Iapetus, the outermost of the large moons, displays a bicoloration so extreme that Giovanni Cassini himself noted in 1671 that it was only visible on one side of Saturn, concluding correctly that the leading hemisphere must be dark and the trailing hemisphere bright. Cassini imagery confirmed the pattern in extraordinary detail. The leading hemisphere is as dark as coal, the trailing hemisphere as bright as fresh snow. The dark material is now understood to be a combination of organic compounds swept up as Iapetus orbits prograde through a diffuse cloud of dark particles, the same cloud that generates reddish material on other outer moon surfaces, modified and amplified by thermal segregation. Dark material absorbs sunlight, heats up, drives ice to migrate to cooler regions, leaving behind a progressively darker surface in a self-reinforcing feedback loop that amplifies the original asymmetry over hundreds of millions of years. Iapetus also possesses a remarkable equatorial ridge reaching 13 kilometers in height and running along the equator for roughly 1,600 kilometers. The ridge's origin is debated. It may be the remnant of an ancient ring system that collapsed onto the moon's equator when its rotation rate was faster, or it may be an expression of internal stresses in the early cooling history of the moon. Either way, it is a structure without a clear analog anywhere else in the solar system. Mimas, the innermost of the larger Saturnian moons, is dominated by the 13-kilometer Herschel crater, giving it an appearance so reminiscent of a certain science fiction icon that the comparison has become unavoidable in any public discussion. But Mimas harbors a genuine scientific mystery of its own. Thermal data from Cassini's infrared spectrometer revealed a bizarre temperature pattern on Mimas' surface. Instead of the uniform gradient from the warm, sun-facing hemisphere to the cold, shadowed hemisphere that simple thermal models predict, The surface shows a Pac-Man-shaped warm region on the leading hemisphere. This anomaly implies that different regions of Mimas's surface have radically different thermal properties, some regions warming and cooling quickly with solar illumination, others holding their temperature with much greater inertia, suggesting differences in surface texture or composition that are not understood from available data. In 2024, analysis of Cassini's gravity and rotation data published in Nature Astronomy provided additional evidence that Mimas may harbor a liquid water ocean beneath its heavily cratered surface, an ocean that formed only within the last 25 million years. If confirmed, Mimas would be the most recently formed ocean world known, its interior still in the process of melting, its surface apparently showing no signs of the geological resurfacing that Enceladus and Titan display. It would mean that ocean worlds are forming around Saturn even now. Cassini's grand finale sent the spacecraft through the gap between Saturn's rings and its cloud tops 22 times between April and September 2017. Those dives allowed direct sampling of ring material and upper atmospheric gases simultaneously, revealing that ring particles, primarily water ice with trace contaminants, are raining onto Saturn's equator at a rate of several thousand kilograms per second, a process called ring rain. The total mass of Saturn's rings, measured by the gravitational effect on Cassini's trajectory, is approximately 40% of the mass of Mimas, remarkably small for such a visually dominant structure. At the current ring rain rate, the rings will disappear within 100 to 300 million years. They appear to have formed within the last 400 million years. Perhaps from the tidal disruption of a moon or the capture and breakup of a comet. The solar system is 4.6 billion years old. We exist in a brief cosmological moment when Saturn's rings are present to see. The grand finale measurements also constrain the deepest mystery of Saturn's interior, its rotation rate. Because Saturn's magnetic field is almost perfectly symmetric about the rotation axis symmetric to within 1 degree, far more symmetric than any other planetary magnetic field, scientists had been unable to determine whether the planet's interior rotates uniformly or differentially. Different tracers gave conflicting answers. The close-in magnetometer measurements from the grand finale established that the symmetry is maintained down to extremely small deviations that a stably stratified layer in the molecular hydrogen envelope could impose on the field regardless of the rotation below. This suggests that Saturn's interior rotation, the rotation of its deep dynamo region, may differ significantly from both the atmospheric rotation and the rotation inferred from its magnetic field. Saturn may be hiding its true spin rate behind a magnetic mask. Cassini's last transmission was received at 7:55 a.m. Pacific Time on September 15, 2017, seconds before the spacecraft entered Saturn's atmosphere, and was torn apart at supersonic speed, its atoms dispersing into the planet it had spent 13 years studying from orbit. The outermost ice giants, Uranus and Neptune, remain the least explored planets in the solar system. Voyager 2 is the only spacecraft ever to have visited either of them, flying past Uranus in January 1986 and Neptune in August 1989, as part of a grand tour trajectory identified in the 1960s by aerospace engineer Gary Flandro while working as a summer student at the Jet Propulsion Laboratory. His calculations showed that a spacecraft launched in the late 1970s could visit Jupiter, Saturn, Uranus, and Neptune in sequence, using each planet's gravity to reach the next. The alignment that made this possible occurs only once every 176 years. Without it, a direct mission to Neptune using chemical propulsion would require approximately 30 years of flight time at trajectories achievable with the rockets of that era. With the alignment, Voyager 2 reached Neptune in 12 years. Uranus proved to be a planet unlike any other in the solar system. Its rotation axis is tilted 98 degrees from the plane of its orbit. Effectively, the planet lies on its side, with one pole pointing roughly toward the Sun and the other pointing away, alternating over the 84-year orbital period. During the Voyager encounter, the South Pole was pointing nearly directly at the Sun, meaning the spacecraft approached from a direction roughly perpendicular to the equatorial plane. Nearly all of its known moons orbit in the equatorial plane, the same tilted plane, suggesting they either formed from material ejected by the same impact that tilted the planet, or were established in their current orbits by tidal evolution thereafter. The magnetic field of Uranus turned out to be even stranger than its orientation. Instead of the dipole field aligned roughly with the rotation axis, the configuration found at Earth, Jupiter, Saturn, and even Mercury, Uranus has a magnetic dipole offset from its center by 0.3 planetary radii and tilted 59 degrees from the rotation axis. The combination of a large offset and a large tilt creates a field geometry with no analog in the solar system. The field is not generated in a small metallic core, as at terrestrial planets, but in a conducting shell of pressurized water and ammonia at intermediate depths, a layer sometimes called the superionic ocean in modern theoretical models, where water molecules dissociate and their oxygen atoms form a solid crystalline lattice, while their protons diffuse freely as a conducting fluid. This exotic state of matter, simultaneously solid and liquid, has been produced in laboratory shock experiments at pressures comparable to those in Uranus's interior. It may be the dominant phase of material in both ice giants, and it may be directly responsible for their bizarre magnetic field geometries. Uranus also presents a profound energy mystery. Jupiter, Saturn, and Neptune all radiate significantly more energy than they receive from the Sun, heat left over from their formation slowly leaking outward over billions of years. Neptune radiates about 2.6 times its absorbed solar energy, but Uranus radiates almost exactly as much energy as it receives. Its internal heat flux is essentially zero, or at least so small that it cannot be detected against the background of absorbed solar radiation. Why a planet otherwise very similar in mass, composition, and formation history to Neptune should have retained essentially none of its primordial heat is deeply unclear. One hypothesis attributes it to the same giant impact that tilted Uranus. If the impact created a thermally stratified interior, a warm layer trapped beneath a cooler one, that stratification could have inhibited convection and effectively sealed the interior heat from escaping, allowing the planet to cool from the outside while remaining warm inside. This would predict that Uranus's interior is warmer than it appears from outside, a prediction not yet testable without an in-situ probe. Voyage 2's brief flyby of Uranus in January 1986, lasting roughly 6 hours at closest approach, discovered 10 previously unknown moons and 2 rings, and returned imagery of the 5 major moons. Miranda, the innermost, proved to be the most geologically complex object in the system. Its surface is a collision of dramatically different terrain types: ancient cratered plains, younger rich terrain, and extraordinary coronae, ovoid or trapezoid-shaped regions bounded by concentric ridges and troughs. Verona Rupes, a cliff on Miranda's surface, is estimated at 20 kilometers in height, making it the tallest cliff known in the solar system. If you fell from the top of Verona Rupes under Miranda's 0.079 gram surface gravity, it would take more than 10 minutes to reach the bottom. Titania, the largest moon, shows evidence of past geological activity in the form of an extensive system of grabens, valleys formed when the crust pulled apart, including the Messina chasmata, a rift system roughly 1,500 kilometers long.
Ariel has the youngest and most heavily resurfaced terrain of any Uranian moon, with smooth plains that appear to have flooded former craters. While Umbriel's surface is the darkest and most ancient, its craters densely packed and largely unmodified since the early solar system. At Neptune, Voyager 2 found a planet dominated by extreme dynamics. Winds in the southern hemisphere reached 2,100 kilometers per hour, flowing westward, opposite to the planet's rotation, making them the fastest sustained winds measured anywhere in the solar system. The source of this atmospheric energy is mysterious. Neptune receives only about 4% as much sunlight as Uranus and 1/900th as much as Earth. Yet its atmosphere is far more active. The answer likely involves Neptune's significant internal heat source.
It radiates 2.6 times more energy than it receives, which drives deep atmospheric convection that interacts with the rapid rotation to generate the extreme jet streams. A large oval storm system, the Great Dark Spot, was observed in the southern hemisphere at a size comparable to Earth, but when the Hubble Space Telescope looked for it in 1994, it had disappeared. New dark spots have since appeared and vanished.
Neptune's weather is transient in a way that Jupiter's is not. Triton, Neptune's largest moon, travels in a retrograde orbit inclined 157 degrees to Neptune's equatorial plane, orbiting in the opposite direction from Neptune's rotation and in a plane tilted steeply relative to the equator. No moon that formed alongside its parent planet could have acquired such an orbit.
Triton is a captured Kuiper Belt object, a body that spent billions of years in the outer solar system before being drawn into Neptune's gravitational reach, probably when it passed close enough for a three-body interaction to dissipate sufficient energy to bind it.
The capture event would have been catastrophic for any original Neptunian moons, as Triton's highly elliptical initial orbit would have swept through the inner system, gravitationally perturbing and ejecting or destroying any satellites that had formed there. The present irregular moons of Neptune, small, dark, and scattered across inclined orbits, are probably the survivors of that disruption. Triton's retrograde orbit is slowly decaying due to tidal friction. The same tidal interaction that is pushing the moon away from Earth is pulling Triton toward Neptune. In approximately 3.6 billion years, Triton will cross inside Neptune's Roche limit, the boundary within which tidal forces exceed the moon's own self-gravity, and will be shredded into a ring system. Voyager 2's observations showed Triton to be a geologically active world, despite its surface temperature of minus 235 degrees Celsius.
The south polar terrain bore dark streaks that Voyager traced to geyser activity. Solar radiation penetrating the transparent nitrogen ice cap heats dark substrate material beneath it, generating nitrogen vapor that builds pressure over months and years before erupting through the overlying ice in plumes, reaching 8 kilometers altitude. The dark material, likely complex organics, is then blown downwind to form the dark streaks.
Triton almost certainly harbors a subsurface ocean. Its size, composition, and thermal history are consistent with significant radiogenic heating, and tidal heating during the circularization of its capture orbit would have provided additional energy. The question is, how much of that ocean survives today? The 2022 Decadal survey placed the Uranus orbiter and probe as the highest priority flagship mission for the coming decade of planetary science. A consensus judgment by the planetary science community representing the first time either ice giant has held that position. The mission concept would deliver a spacecraft to Uranus orbit for at least 4 years, conducting comprehensive mapping of the atmosphere, interior magnetic field ring system, and moon system, while releasing an atmospheric probe to descend through the upper atmosphere and measure composition and structure at depths beyond the reach of remote sensing. The probe would likely function for only 1 to 2 hours before being destroyed by increasing pressure and temperature. But those hours would provide the first direct measurements of Uranus's atmospheric structure below the cloud tops, information that would constrain interior models for decades. The mission is currently in study phase with a potential launch window in the early 2030s using Jupiter gravity assist to reach Uranus by the early 2040s. Deep in the ice giant's interiors, theoretical models predict the existence of diamond rain, carbon atoms squeezed out of methane under pressures of millions of atmospheres, crystallizing into diamonds that then sink toward the core. Laboratory experiments using laser-driven shock compression to generate momentary pressures comparable to those deep in an ice giant's interior have directly observed this process. X-ray measurements show that carbon atoms separate from methane and form diamond structures within nanoseconds of shock application. At the temperatures and pressures within Uranus or Neptune, these diamonds may grow to considerable size before sinking to rest atop the dense cores. The prediction implies that the interiors of the ice giants contain layers of diamond precipitation, oceans of liquid diamond in which solid diamond pieces float, analogous to water ice floating on liquid water, but composed of pure carbon at conditions that defy ordinary intuition. No spacecraft has yet probed to the depths where this occurs. The question of what actually exists in the deep interiors of the ice giants is one of the most consequential unknowns in planetary science. Among all the objects in the solar system, Jupiter remains in a category of its own. It contains more mass than all other planets combined, twice the mass of all other planets together, generates a magnetic field 14 times stronger than Earth's, and hosts a storm system. The Great Red Spot that has persisted since at least the 17th century, when astronomers first recorded it. Its influence extends throughout the solar system. Its gravitational pull shepherds the asteroid belt, deflects long-period comets that might otherwise strike the inner planets, and participated actively in shaping the orbits of every other body in the solar system during the first 100 million years of its existence. Jupiter is not merely the largest planet, it is the gravitational spine around which the architecture of the solar system was organized. The first spacecraft to achieve orbit around Jupiter was Galileo, which arrived in December 1995 after a 6-year journey that included a deliberately chosen trajectory past Venus and twice past Earth to accumulate the necessary speed. Galileo released an atmospheric probe before orbital insertion, the only probe ever to enter Jupiter's atmosphere, which descended for 57 minutes before being destroyed by increasing pressure and temperature. The probe found winds gusting to 530 kilometers per hour, a severe depletion of water vapor relative to solar abundance, and higher concentrations of noble gases than any model had predicted. The wind speeds and noble gas abundances suggested that the probe had entered a hotspot, a region of locally cleared atmosphere above a descending column of dry air, and that the rest of Jupiter's atmosphere might look quite different. This single anomalous entry point constrained Jovian models for 15 years until Juno's microwave radiometer could measure the atmospheric composition globally. Galileo also discovered that 3 of the 4 Galilean moons harbor subsurface liquid water. Europa's ocean was already strongly suggested by magnetometer data from Voyager. Galileo confirmed it by detecting induced magnetic fields generated by the interaction of a conducting layer with Jupiter's rotating magnetic field in the vicinity of Europa, Ganymede, and Callisto. Ganymede's ocean was the most surprising. Ganymede is larger than Mercury, making it the largest moon in the solar system, and its ocean is buried beneath an ice shell, perhaps 800 kilometers thick, sandwiched between layers of high-pressure ice. The ocean's salt water interacts with Jupiter's magnetosphere to create a subtle distortion in Ganymede's own magnetic field,
which Ganymede uniquely possesses, generated by a dynamo in its iron core, and this distortion allowed Galileo to infer the ocean's presence. The Hubble Space Telescope later confirmed the ocean by observing periodic rocking of Ganymede's auroral ovals in response to Jupiter's magnetic field, a rocking whose amplitude is damped by the conducting ocean beneath the ice. The Juno spacecraft entered Jupiter's orbit on July 4, 2016, after a 5-year journey. It followed a highly elliptical polar orbit, swooping to within 4,000 kilometers of Jupiter's cloud tops every 53 days before retreating to a safe distance beyond the most intense radiation belts. At closest approach, Juno's radiation exposure is comparable to receiving 1 million chest X-rays in under an hour. The spacecraft's electronics are protected within a titanium vault, a radiation-hardened central electronics box with walls 1 centimeter thick, containing 20 kilograms of titanium shielding that reduces the radiation dose to the internal hardware by a factor of about 800. Even so, the cumulative radiation exposure over the mission is expected to significantly degrade some of the spacecraft's electronic components. The Juno team monitors instrument health continuously and operates on an extended mission timeline that accounts for progressive performance degradation. Juno's findings on Jupiter's interior restructured planetary formation theory. The core, a concept that seemed straightforward before the mission, turned out to be a diffuse, extended region rather than a compact rocky sphere. Instead of a dense central mass, perhaps 10 to 20 Earth masses in size, Juno's gravity science data indicate that heavy elements are distributed throughout approximately the inner 30 to 50% of Jupiter's radius, mixed into the surrounding metallic hydrogen rather than concentrated at the center. This configuration, sometimes called the dilute or fuzzy core, is inconsistent with most standard formation models. One explanation gaining traction is a giant impact hypothesis. Early in Jupiter's history, a planetary embryo roughly 10 times the mass of Earth struck the young planet and stirred the core material outward through the metallic hydrogen envelope. Such an impact would have been consistent with the turbulent dynamics of the early solar system, and simulations show that the resulting chemical mixing would have persisted largely intact over billions of years of subsequent evolution. The magnetic field, measured at unprecedented precision by Juno's magnetometer, the most accurate flux gate magnetometer ever flown on a deep space mission, revealed a structure far more complex and asymmetric than the relatively simple axial dipole assumed by previous models. The field is dominated by a region of intense flux concentration in the northern hemisphere, centered near longitude 2000 degrees, that has been named the Great Blue Spot by analogy with Jupiter's atmospheric features. Within this region, the field strength reaches 7.8 Gauss, more than 10 times the global average of 0.6 Gauss. No counterpart of comparable strength exists in the southern hemisphere. This north-south asymmetry implies that Jupiter's dynamo, the convective metallic hydrogen fluid motion that generates the field, operates differently in the two hemispheres, possibly reflecting differences in temperature, composition, or flow patterns that are not yet understood. Tracking the magnetic field's evolution over the course of the Juno mission has already revealed measurable change in the field structure at the Great Blue Spot. Secular variation in Jupiter's magnetic field observed for the first time. The atmospheric dynamics of Jupiter, probed by the microwave radiometer and camera system, revealed the same banded structure visible from Earth to persist to remarkable depth. The jet streams that bound the atmospheric zones and belts, the alternating light and dark bands, extend downward at nearly constant velocity to pressures of approximately 2000 bars, corresponding to a depth of roughly 3000 kilometers below the visible cloud tops. Below that depth, the rotation becomes more uniform, more solid body-like, as the increasing electrical conductivity of the metallic hydrogen suppresses differential rotation through magnetohydrodynamic braking. The transition between the weather layer and the underlying interior occurs gradually, not at a sharp boundary. And the exact location and nature of that transition is one of the questions Juno's continued operations are addressing. The polar regions of Jupiter, never previously observed at close range from a polar orbit, proved to be among the most visually striking environments in the solar system. Instead of the orderly banded structure that dominates at low latitudes, Jupiter's poles are covered with densely packed cyclonic storms, each hundreds to thousands of kilometers across, arranged in stable geometric configurations. The North Pole hosts a central cyclone surrounded by 8 peripheral cyclones in an octagonal arrangement. The South Pole has a central cyclone ringed by 5 others in a pentagonal arrangement. These polygonal arrays have persisted with remarkable stability across years of Juno observations, defying the expectation that cyclones would merge over time as they do on Earth and in most atmospheric simulations. The stability appears to be maintained by a wave mechanism that keeps the peripheral vortices in resonance, prevented from merging with the central cyclone by a phenomenon called the Rossby wave propagation barrier. But the detailed dynamics that stabilize the specific polygonal numbers seen at each pole are not fully reproduced in current atmospheric models. Juno also detected lightning in Jupiter's atmosphere in a way that finally resolved a long-standing puzzle. Voyager had detected radio signals consistent with lightning, but the precise frequencies differed from what terrestrial models predicted. Juno's radio receivers, operating at the right frequencies and with much higher time resolution, confirmed lightning at rates and energy levels broadly similar to terrestrial thunderstorms, but concentrated at high latitudes rather than at the equator, where Jupiter's solar heating is most intense. On Earth, thunderstorms cluster near the equator because that is where the most solar energy enters the atmosphere, driving convection. On Jupiter, the equatorial regions are suppressed by the overlying heat from the deep interior, while the poles receiving less solar input are more convectively active. Juno's ultraviolet spectrograph captured a transient flash of near-ultraviolet emission above a thunderstorm complex, interpreted as a sprite, a type of electrical discharge that occurs in the upper atmosphere above powerful storms. On Earth, sprites are red because they excite nitrogen. Jupiter's hydrogen-dominated upper atmosphere would produce sprites that glow blue or violet, which is exactly what the ultraviolet spectrograph detected. Juno's extended mission, running through 2025, included close flybys of 3 of the Galilean moons that will be studied in far greater detail by future missions. The Ganymede flyby in June 2021 passed within 138 kilometers, closer than any spacecraft had approached since Galileo, returning images at 1 kilometer per pixel resolution. The Europa flyby in September 2022, close to 352 kilometers, the nearest approach to Europa since 2000, returning imagery that revealed new structures in the chaos terrain and rich complexes that will serve as targeting references for the Europa Clipper mission. Europa Clipper launched in October 2024 aboard a SpaceX Falcon Heavy rocket, beginning a 5.5-year journey to Jupiter that will deliver it to Europa orbit, or more precisely a Jupiter orbit with repeated Europa flybys by April 2030. The spacecraft carries 9 science instruments, including a magnetometer, to confirm and characterize the ocean, an ice-penetrating radar to map the ice shell thickness and identify any subsurface water lenses near the surface, an infrared spectrometer to map surface composition, and a mass spectrometer to sample the tenuous atmosphere and any plume material.
The mission will conduct approximately 49 Europa flybys at altitudes as low as 25 kilometers, building a global map of the surface at 50-meter resolution and determining whether Europa's ocean has the chemical conditions necessary for life. Io, the innermost Galilean moon, presents an entirely different kind of extreme. Squeezed between Jupiter's powerful gravity and the gravitational influence of the other Galilean moons in a Laplace resonance, a configuration where the orbital periods of Io, Europa, and Ganymede are in a 1:4 ratio. Io is the most volcanically active body in the solar system, generating roughly 100 times more heat per unit area than Earth. Its surface is continuously resurfaced by sulfur and silicate lavas, with plumes reaching hundreds of kilometers altitude and volcanic mountains exceeding 18 kilometers in height. Loki Patera, a lava lake roughly 200 kilometers across that brightens and dims in a pattern suggesting periodic overturning of the lava crust, has been monitored from Earth since Voyager's discovery in 1979. Juno made 2 close Io flybys in late 2023 and early 2024, returning the highest resolution global imagery of Io's surface since Galileo, including detailed views of active eruption sites and new lava flows that had modified the surface since the last close observations. The images showed Io's surface in the process of transformation, a world being continuously destroyed and rebuilt by the internal heat generated by tidal forces reaching all the way from Jupiter. Every spacecraft described here operated at the absolute boundary of human engineering capability. They were built to function in radiation environments that would destroy ordinary semiconductor electronics within hours. Environments created by the intense magnetic fields and energetic particle populations of the outer planets, particularly Jupiter, whose radiation belts are 10,000 times more intense than Earth's Van Allen belts at their most energetic. The electronics aboard Juno and Galileo are radiation-hardened variants of standard components, manufactured through specialized processes that reduce their sensitivity to ionizing radiation and housed within shielding vaults that absorb the most energetic particles. Even so, the cumulative dose across a multi-year mission at Jupiter reaches levels that would be considered catastrophic in terrestrial electronics without these precautions. They communicate across distances measured in light hours using radio transmitters drawing a few tens of watts, less power than a ceiling fan, focused by parabolic high-gain antennas into pencil-thin beams aimed at Earth from hundreds of millions of kilometers away. The signals arrive at the receiving dishes of the Deep Space Network, 70-meter radio telescopes at Goldstone in California, near Madrid in Spain, and near Canberra in Australia. With power densities so faint that a single photon of signal arrives only every few seconds in some cases. The data rates achievable under these conditions are modest by any standard comparison. Cassini's final transmissions from Saturn arrived at 27,000 bits per second. A modern home internet connection transmits roughly 1 million times faster. The complete scientific archive of the Voyager 2 Neptune encounter, 70 gigabits of data, was transmitted over a period of months at a rate of 21,600 bits per second. The maximum achievable at Neptune's distance using the technology of 1989 and the receiving capabilities of the largest antennas available. Navigation across the solar system is performed by tracking the Doppler shift and time delay of radio signals with precision measured in fractions of millimeters per second in velocity and meters in position at ranges of billions of kilometers. The mathematics of orbital mechanics, Newton's laws of gravity refined by Einstein's general relativity, applied to a solar system in which every significant body exerts gravitational influence on every spacecraft, is implemented in software at the Jet Propulsion Laboratory that can predict spacecraft positions years in advance with errors of tens of meters. Trajectory correction maneuvers, performed by firing thrusters for fractions of a second, achieve velocity changes of a few millimeters per second that, accumulated over months of flight, redirect a spacecraft from one planetary target to another, with an accuracy that has no precedent in any other field of engineering. The gravitational assist maneuver, the technique of using a planet's orbital motion to accelerate or decelerate a spacecraft through a precisely calculated close flyby, is the foundational technique that made the Grand Tour possible and that underlies the design of virtually every outer solar system mission flown since the 1970s. Several of these spacecraft outlived their planned missions by years or decades. Cassini was approved for a 4-year primary mission and operated for 30. Dawn was designed for a 3-year mission at Vesta and Ceres combined and operated for 11 years before its fuel ran out. Voyager 2, launched on August 20, 1977, crossed the heliopause, the boundary between the Sun's plasma and the interstellar medium, in November 2018, 41 years after launch. As of 2024, it is more than 22 billion kilometers from the Sun, still transmitting data, still powered by thermoelectric generators, converting the decay heat of plutonium-238 into electricity at approximately 200 watts, a quantity that decreases by about 4 watts per year as the plutonium decays. The mission team powers down instruments one by one as the available electricity decreases, hoping to maintain at least minimal contact through the 2030 streaks before the power budget drops below the minimum required to operate any science instrument and maintain the transmitter simultaneously. Voyager 1, launched 2 weeks after Voyager 2 and now more than 24 billion kilometers from the Sun, is the most distant human-made object in existence. Both carry a gold-plated copper disc, the Voyager Golden Record, containing sounds, music and images from Earth, selected and assembled by a committee that included Carl Sagan, encoded in a format designed to be decodable by any civilization with sufficient technical sophistication to recover the probe. It is an act of communication into geological time. The past 20 years have witnessed a transformation in the scale and ambition of outer solar system science. When Cassini launched in 1997, the subsurface oceans of Europa were hypothesized but unconfirmed. Enceladus was a geologically unremarkable icy moon. Titan's methane lakes were theoretical predictions, and the composition of asteroids was known only from the meteorites that survived atmospheric entry and reached terrestrial laboratories, a sample biased heavily toward the most mechanically durable objects. The missions described here have changed the inventory of potentially habitable environments from a single planet to at least 8 moons, a dwarf planet, and possibly even an asteroid. They have delivered material from asteroids directly into laboratories, eliminating the selection bias of meteorite collections. They have demonstrated powered flight on another world, produced oxygen from another planet's atmosphere, mapped the interior of the solar system's largest planet, and sampled the plumes of a moon that may have a living ocean beneath its ice. What these missions have not yet done is find life. That question, whether any of the habitable environments identified in the solar system are actually inhabited, remains entirely open. The detection of molecular hydrogen in Enceladus's plumes is consistent with life, but does not require it. The organic compounds in Ryugu are consistent with biological building blocks, but formed abiotically. The methane on Mars detected from orbit in amounts that vary seasonally has multiple possible abiotic explanations and has not been definitively confirmed by surface measurement. Every piece of evidence is ambiguous, and ambiguity is the correct situation in science before decisive experiments have been performed. The decisive experiments, sample return from Mars analyzed in full terrestrial laboratory capability, extended plume sampling at Enceladus, an in situ ocean probe at Europa,
are either already in progress in development or scheduled for the coming decades. The question of whether life exists elsewhere in the solar system is not simply a scientific question, though it is a question about the nature of life itself, whether it is a singular event, a cosmic accident that happened once on one planet in one solar system, or a robust chemical process that recurs wherever the necessary conditions are met. If life exists in the ocean of Enceladus, having originated independently from terrestrial life, then life is almost certainly common throughout the universe, because the conditions on Enceladus are not exceptional. They exist wherever icy moons orbit large planets, and large planets with icy moons are known to be common throughout the galaxy. If life does not exist in the ocean of Enceladus, despite the presence of liquid water, chemical energy, and organic compounds, then the origin of life is harder, rarer, or more constrained than the conditions at Enceladus suggest, and the implications for the prevalence of life in the universe are more sobering. The outcome of this question, the most fundamental scientific question humans have ever posed, may be answerable within the lifetimes of people now living. The instruments needed to detect microbial life in a plume sample or in a Martian rock core or in the ocean water of Enceladus or Europa exist. The spacecraft that will deliver those instruments are being built or will be built. The trajectories have been calculated. The only remaining variable is whether the human civilizations operating these missions sustain the investment of time, money, attention, and technical expertise needed to carry them to completion, and then wherever the data leads to follow it. We have been building instruments to study the solar system for 60 years. We have been asking these questions about the other worlds around our star, about what they are made of and how they formed and whether anything lives on or in them. For much longer than that, the solar system we inhabit is not the simple ordered clockwork of planets in elliptical orbits that it appeared to be when the first spacecraft left Earth. It is a complex, active, chemically rich environment, full of oceans and geysers and organic chemistry and ongoing geological processes, most of it unexplored in any detail, much of it apparently meeting the minimum conditions for the existence of life. Every mission we have sent has expanded the picture, every mission planned will expand it further. The work continues, the spacecraft are en route. The data is coming in one photon at a time across the dark between the worlds. And somewhere in the data, in the mass spectra from Enceladus's plumes, in the rock cores from Jezero crater, in the radar returns from Europa's ice, there may be the answer to the question that drives all of it. We are paying attention. We are keeping the antennas pointed. We want to know. No object in the solar system better illustrates the difference between distant observation and close encounter than Pluto. For 85 years after its discovery in 1930, Pluto was known primarily as a point of light, its size uncertain, its surface composition inferred from spectra, its moons invisible to all but the most capable telescopes. Astronomers knew it was cold, small, and distant. They knew it had an atmosphere of nitrogen and methane that thickened slightly as it approached the sun and then collapsed back to the surface as it receded. They knew it had a large moon, Charon, so large relative to Pluto that the two bodies orbit each other around a common center of gravity located in the space between them, making Pluto-Charon technically a binary system rather than a planet and a satellite in the conventional sense. Beyond that, Pluto was a mystery, a dot. New Horizons launched in January 2006 on a trajectory so fast, 16.3 kilometers per second, faster than any spacecraft had previously left Earth, that it crossed the orbit of the Moon in just 9 hours. It flew past Jupiter in February 2007, using the giant planet's gravity for a further velocity boost, and spent the next 8 years in cruise mode, instruments powered down, the science team waiting.
The encounter with Pluto lasted roughly 7 hours of closest approach on July 14, 2015, during which New Horizons passed within 12,500 kilometers of Pluto's surface. The resolution of the best images, better than 80 meters per pixel, revealed a world of astonishing complexity. The most immediately striking feature was the Tomba Regio, a heart-shaped region roughly 1,500 kilometers across that became the defining image of the mission. The western lobe of the heart, later named Sputnik Planitia, is a vast nitrogen ice plain occupying what appears to be an ancient impact basin about 3 kilometers below the surrounding terrain. The plain is divided into polygonal cells roughly 30 kilometers across by a network of shallow troughs, a convection pattern caused by nitrogen ice at the surface being slightly warmer at depth than at the top, creating slow overturn cells that rise and sink on timescales of thousands to hundreds of thousands of years. The surface of Sputnik Planitia is the geologically youngest terrain on Pluto. It is virtually free of impact craters, indicating that it has been completely resurfaced within the last perhaps 10 million years. On a world 4.5 billion years old, 10 million years is essentially yesterday. The western mountains, fringing Sputnik Planitia, rising 3 to 4 kilometers above the plain, are composed not of nitrogen or methane ice, too soft under Pluto's conditions to support such topography, but of water ice. Pluto is cold enough that water ice behaves as rock, rigid, strong, capable of sustaining mountain ranges and cliff faces. This makes water ice Pluto's bedrock, just as silicate rock is the structural material of the terrestrial planets. The volatile ices, nitrogen, methane, carbon monoxide, are a thin veneer on top of this water ice bedrock, redistributed by seasonal and geological processes. Some of those processes include apparent cryovolcanic features. 2 large dome-like mountains with possible central depressions, Wright Mons and Picard Mons, that have been tentatively identified as cryovolcanic constructs, mounds built by the eruption of slurries of water ice, ammonia, or other volatile materials from the interior. If confirmed, they would make Pluto another body in the outer solar system, with internally driven geological activity driven by a subsurface heat source, possibly a remnant liquid water ocean insulated by the overlying ice. Pluto's atmosphere, though tenuous surface pressure, roughly 10 microbar, about 100 thousandths of Earth's sea level pressure, extends surprisingly high above the surface. New Horizons observed the atmosphere backlit by the sun during the departure phase of the flyby, revealing a series of haze layers stacked up to 200 kilometers altitude. The haze is composed of tholins, the same complex organic polymers found in Titan's atmosphere, produced when ultraviolet radiation breaks apart methane and nitrogen molecules and the fragments recombine into larger structures. The tholins settle to the surface and tint Pluto's terrain in the reddish and brownish hues visible in the mission images, a chemistry that on Titan has been discussed as potentially relevant to prebiotic organic synthesis. On Pluto, the temperatures are lower and the energy inputs more limited, but the same basic photochemistry operates. Pluto is manufacturing complex organic molecules continuously, depositing them across its surface like a slow red snow. Charon, observed at close range for the first time during the flyby, proved to be geologically distinct from Pluto. Its north pole is covered by a large red-brown region, informally named Mordor Macula, that is almost certainly composed of tholins. Methane escaping from Pluto's atmosphere travels to Charon, is trapped by the colder polar temperatures during the long polar winter, and is then chemically transformed by radiation into dark organic compounds. Charon imports its organic chemistry from its binary partner. The rest of Charon's surface is a mixture of ancient cratered terrain and tectonically modified plains cut by a canyon system,
Serenity Chasma that stretches more than 1,600 kilometers and reaches depths of 9 kilometers, suggesting that Charon's interior expanded as it froze, cracking the surface. Whether Charon once had a liquid water interior depends on its early thermal history, which in turn depends on how the Pluto-Charon binary formed, probably through a giant impact similar to the event thought to have created the Earth-Moon system, but occurring in the outer solar system among Kuiper Belt objects. New Horizons continued past Pluto and on January 1st, 2019, flew past a small Kuiper Belt object called Arrowcot, a contact binary 2 lobes that had gently merged from a slowly coalescing cloud of material rather than colliding at speed. Arrowcot's smooth reddish surface and its formation mechanism provide direct evidence for the accretion process that built the planetesimals of the outer solar system in the first place. Unlike the violent collisional agglomeration invoked for inner solar system bodies, the outer solar system apparently accumulated its building blocks through gentle collapse of gravitationally bound particle clouds, a process that preserves the primordial chemical composition far better than high-energy impacts. Arrowcot may be the most pristine, least processed solid object ever observed at close range by a spacecraft. New Horizons is now in the outer Kuiper Belt, approximately 57 astronomical units from the Sun, still operational and still detecting the faint ultraviolet glow of the cosmic background, measurements that will constrain models of the diffuse interstellar radiation field. Its power source, like Voyager's, is a radioisotope thermoelectric generator running on plutonium-238, and it is expected to remain operational into the mid-2030s. The past decade has also brought a capability to the study of the solar system from Earth orbit that planetary scientists had not anticipated in its breadth. The James Webb Space Telescope, launched in December 2021 and fully operational by the summer of 2022, has demonstrated remarkable sensitivity for solar system observations despite being designed primarily for extragalactic and exoplanet science. Its near and mid-infrared spectrographs have mapped the chemical composition of Titan's atmosphere at resolutions and wavelengths previously inaccessible, detecting previously unidentified molecules in the northern polar region, where storms and chemistry were ongoing during the telescope's first observations. It has observed Jupiter's auroras and great red spot at near-infrared wavelengths, revealing thermal structure inaccessible to ground-based observatories. It has detected carbon dioxide ice on the surface of Enceladus, and its spatial resolution is sufficient to resolve the plumes directly. It observed the DART impactor's debris cloud at Dimorphos, the first time a spacecraft deliberately and successfully altered the orbit of a planetary body. The Dimorphos moonlet of the asteroid Didymos, demonstrating that a kinetic impactor could redirect a hazardous asteroid if detected sufficiently in advance. DART struck Dimorphos in September 2020 and shortened its orbital period around Didymos by approximately 33 minutes, more than 10 times the minimum change required to demonstrate the technique's feasibility, because the impact ejected so much material from the surface that the ejector's momentum carried far more deflection than the spacecraft's own impact. The lesson: the reaction of the target body to an impact is as important as the impact itself, and the loosely consolidated rubble pile structure of many near-Earth asteroids may actually make them easier to deflect than predicted. The ESA mission Hera, launched in October 2024, is en route to Didymos and Dimorphos to conduct a detailed post-impact survey of the effects of the DART strike, measuring the mass density and internal structure of Dimorphos, mapping the surface changes produced by the impact and characterizing the crater. The data will calibrate planetary defense models for decades and establish the quantitative relationship between impact conditions and deflection outcome for a real planetary body. Together, DART and Hera represent humanity's first actual,
Not simulated, not modeled, not estimated attempt to change the trajectory of a natural solar system object, and its first confirmation that such a change is achievable with currently available technology. This is an entirely new category of human action in the solar system, not merely observing it, not merely visiting it, but deliberately reshaping part of it. The cumulative picture, assembled by 60 years of solar system exploration, is one of a place far more dynamic, chemically rich, and geometrically varied than any pre-spacecraft conception suggested. The solar system contains not one ocean, but at least 8 suspected liquid water environments on bodies ranging from the size of a city to the size of a planet. It contains active volcanoes on a moon of Jupiter and a moon of Neptune. It contains nitrogen geysers on Pluto and Triton. It contains methane lakes on Titan, diamond-producing interiors in the ice giants, and the organic building blocks of life on a primitive asteroid. It contains a storm that has persisted for hundreds of years, a set of rings that are geologically younger than the dinosaurs, and a magnetic field so strange that we have no adequate model for how it forms. None of this was known with certainty before spacecraft visited. All of it will be understood in greater depth or overturned entirely by the missions being built right now, or by the spacecraft that are already flying toward their destinations across the dark. The engineering disciplines required to operate interplanetary spacecraft have generated technological developments whose value extends far beyond space exploration. The need for ultra-miniaturized, radiation-hardened electronics drove advances in semiconductor manufacturing that found applications in medical devices, aviation avionics, and high-reliability computing. The thermal management techniques developed to protect spacecraft from the temperature extremes of deep space, surfaces that must simultaneously radiate excess heat in some directions and absorb as little solar energy as possible in others, contributed to the development of modern insulating materials. The software systems that manage fault detection, isolation, and recovery on spacecraft operating billions of kilometers from Earth. Spacecraft that must diagnose their own failures and take corrective action without waiting the hours it would take for a radio signal to reach Earth and return, represent some of the most sophisticated autonomous control systems ever developed. Every deep space mission is also an engineering experiment, and the lessons accumulate across decades. The international nature of this exploration is easily overlooked in any narrative that focuses on individual missions. Bepi Colombo is a partnership between Europe and Japan. Cassini-Huygens was built by NASA and the European Space Agency jointly, with contributions from Italy's Space Agency for the main antenna. The DART mission that redirected Dimorphos is being followed up by Hera, a European spacecraft. Dawn's instruments included European contributions. Mascot, which explored Ryugu, was built in Germany and France. The Deep Space Network, that provides communication and navigation support for spacecraft from multiple agencies, operates under a data-sharing arrangement with the European Space Tracking Network and the Japanese Yasuda and Uchinora stations. No individual nation can sustain the full breadth of interplanetary exploration alone, and the scientific community that analyzes the returned data is global in composition, regardless of which nation built the spacecraft. Papers analyzing Hayabusa 2 samples have been authored by teams from Japan, the United States, Germany, France, Canada, and several other countries. The knowledge produced by these missions belongs, in a practical and meaningful sense, to the species rather than to any of its political subdivisions. The pace of discovery has accelerated in the past decade in ways that suggest the coming decades will be even more productive. The combination of improved launch vehicles, the Falcon Heavy, which can deliver larger spacecraft to the outer solar system than anything previously commercially available, with more capable instruments, more efficient power sources, and computational tools for data analysis that did not exist 10 years ago, means that missions now achievable were not achievable even recently.
The Europa Clipper is the largest planetary science spacecraft NASA has ever built.
The Dragonfly rotorcraft will be the most mobile surface explorer ever deployed beyond the inner solar system. The Uranus orbiter and probe, when it flies, will carry instrument packages designed using knowledge that did not exist when Voyager 2 flew past in 1986. Each generation of missions builds on the last, informed by its discoveries, equipped with tools its predecessors could not carry, aimed at questions its predecessors could only raise. The solar system is the one place in the universe where we can actually go, where we can touch the rocks, sample the water, measure the fields, and put instruments directly into the environments we want to study. It is our laboratory, our field site, our nearest approximation to the full diversity of planetary environments that the universe contains. What we learn here about how planets form and evolve, about how oceans persist under ice, about how organic chemistry scales from interstellar space to biological complexity, is the foundation for understanding the billions of other solar systems now known to orbit other stars in the galaxy. The questions are ultimately about the universe. The solar system is where we are positioned to begin answering them. The spacecraft continue outward, the data continues arriving. The models continue being revised and extended and occasionally discarded entirely in the face of evidence that demands something better. This is science proceeding as it should, not confirming what was already believed, but finding that reality is consistently more interesting, more varied, and more amenable to inquiry than any prior expectation suggested. There is no indication that this pattern will end. The solar system has absorbed 60 years of intense robotic investigation and still offers more open questions than closed ones. It is not running out of surprises, it is not even close. There is a dimension to this story that the technical vocabulary of orbital mechanics and spectroscopy tends to obscure: the human time dimension. The Voyager spacecraft were designed by engineers whose careers began in the 1950s and 1960s, who retired long before the missions ended, whose grandchildren are now among the scientists analyzing the data. The New Horizons team proposed the mission in the early 1990s, watched it get cancelled once, and then revived, spent a decade building it, waited 8 years in cruise, watched the encounter in 2015 with the intense emotion of people who had given a significant fraction of their professional lives to a single rendezvous. The Europa Clipper team includes scientists who wrote the first papers about Europa's ocean in the early 1990s and are now building the instruments that will test those early inferences. Science at this scale is multi-generational in the most literal sense. The missions also generate knowledge that compounds across time in ways that were not predictable at the moment of design. Cassini's discovery that Enceladus has an ocean changed the scientific justification for the Europa Clipper mission, a mission conceived before Enceladus was known to have an ocean, by demonstrating that subsurface oceans in the outer solar system are not an exotic exception, but a common feature of icy moons. The Hayabusa 2 amino acid results informed the selection of science instruments for future asteroid missions that were in planning at the time of publication. The InSight Marsquake data changed the interior structure models used to interpret Perseverance's gravity and atmospheric measurements. Each mission reconfigures the scientific context for all subsequent missions in ways that cascade forward into planning decisions made decades later. This is the compounding structure of scientific knowledge. Each measurement creates the context for the next measurement. The solar system we will understand in 50 years is not simply the solar system we understand today with more facts added. It will be a different conceptual structure, organized around questions and principles that do not yet exist, informed by discoveries not yet made, built on spacecraft not yet designed. The history of planetary science is a history of successive conceptual revolutions, each one made possible by the one before it. The next revolutions are already in the data, waiting to be recognized.